Hello, everyone. Welcome to another virtual training by the Sustainable Material Management Extreme Events Reconnaissance Organization, or SUMMEER for short. My name is Hiba Jalul, and I am a PhD candidate in Civil and Environmental Engineering and a SUMMEER Graduate Research Assistant. And in this module, I will be presenting the main identified data needs for quantitative sustainable disaster debris management based on an extensive review of the existing literature. In this presentation, I'll start with a background where I will share the identified critical aspects impacting the feasibility of disaster debris reuse or recycling. Then I will explain the methodology followed in the literature review process. Following that, I'll be presenting the results in terms of the identified data needs for each aspect or field of study. And finally, I will end with how the findings are disseminated and how they are validated and extended. Starting with the background, 6 aspects have been identified as the most critical for sustainable management of disaster debris. The amount and composition of the generated debris, which are critical design factors during different phases of the debris management planning, and are key determinants of how much debris can be feasibly recycled, the required recycling rate, and the need for additional recycling facilities. Second, the availability of temporary debris management sites, which provide a buffer and space to store, sort, and process the debris before any further treatment. Limited and insufficient number of such sites for storing and separating recyclables has been reported as one of the major barriers for recycling. Hazards and environmental concerns. As the sustainable management of disaster debris requires the identification of the potential hazards present in the debris stream, along with the minimization of the corresponding negative impacts that the debris management system leaves on the environment. Economics. The cost of managing disaster debris can be substantial. As such, economic viability and cost efficiency are vital for the sustainable management of disaster debris. Fifth, social considerations. Since a sustainable disaster debris management system considers not only the technical aspects, but also the different social concerns and priorities of the vulnerable disaster-affected communities. Finally, funding policies, as the scope and nature of the funding mechanisms can substantially impact the extent of recycling, as these dictate the eligibility for reimbursement of the debris management costs. In order to effectively implement a sustainable debris management system, all of these aforementioned aspects require a thorough database assessment. What's the problem then? Existing studies in the field of disaster debris management have not comprehensively delineated the data and analysis requirements for quantitative assessment of sustainable debris management practices, and they are typically do not provide a holistic perspective. Prior studies generally are qualitative in nature, and quantitative studies often focus on a single aspect of the debris management process. Therefore, we try to address the current knowledge gaps by identifying the data required to inform sustainable disaster debris planning and management by systematically reviewing the existing literature. In addition, since the data requirements are often time-sensitive in the management of post-disaster debris, there was also a need to characterize the identified data based on their time and duration of availability. This brings us to the methodology followed. An extensive literature review was conducted to obtain and synthesize data requirements for sustainable debris management using a systematic search strategy. Google Scholar and Web of Science were utilized to identify all relevant literature. In addition to academic articles, reports published by governmental organizations and agencies, such as FEMA and EPA, were collected. The review process resulted in the selection of 110 documents spanning the time period of 2000 till 2021 and ranging across various disciplines, including disaster response and recovery, waste management, civil engineering, public policy, social sciences, and economics. Selected documents were examined in detail and all relevant information was extracted and further organized in a metadata set table. Information from the metadata set was used to identify the different types of data needed to assess each of the 6 aspects affecting the feasibility of sustainable debris management. Data characterization was conducted using a 4-phase data collection and planning framework, directly aligned with the recovery continuum presented in the National Disaster Recovery Framework established by FEMA in 2011. This framework is composed of the pre-disaster phase, response phase, short-term recovery, and long-term recovery phase. Pre-disaster data are available regardless of the occurrence of a disaster event. These data structures are mostly used in the forecasting and guiding pre-incident planning to increase community preparedness. Post-disaster response phase data are generated in the immediate aftermath of a disaster event. We're talking about days or weeks after a disaster event, and are often available until debris is cleared to facilitate the provision of emergency services. As for the data associated with the short-term recovery phase, these are generated during the debris collection, transportation to temporary debris management sites, and storage at temporary debris management sites, as well as any direct allocation to common waste management facilities, such as transfer stations, recycling facilities, and landfills. The duration during which this data is collected is usually weeks to months after a disaster event. And lastly, the long-term recovery data are available during the disaster debris treatment and recycling phase, along with the disposal of residual debris. Following the methodology that I just explained, we were able to reach the following findings. Of the 6 aspects that control the extent of debris reuse or recycling, the highest number of research studies was identified for debris quantity and composition estimation. The analysis methods provided in the literature range from general formulas, such as the one developed by FEMA and the U.S. Army Corps of Engineers, computer models, which are developed based on historical data of debris quantities generated by past disaster events, such as Hayes' MH and the iWaste tool, statistical or mathematical models among a number of correlating parameters, including exponential regression models, Bayesian inference, and basic unit approaches. And lastly, remote sensing techniques, utilizing aerial, drone, and satellite imagery, which have been used to timely and efficiently assess the damages in large areas following a disaster event, especially when collecting ground-based information is logistically challenging and potentially dangerous. Upon detailed analysis of the debris amount and composition related studies, data needs are grouped into 13 categories. The first category covers demographics, which includes data such as population count or density in the studied area. The second category covers vegetation data, such as the vegetation cover, tree density, percentage tree cover, tree biomass, tree canopy, average tree height, proportions of tree cover in hardwoods versus palms, and cropland area. The third category covers urban data, such as the housing density, density of commercial development, urban area ratio, the number of households, and the number of dwellings. Fourth, the community-level building information data category, which covers data such as the categories of buildings, the number of buildings by a specific occupancy class, the average area of each dwelling, the number of low-rise buildings, and the total floor area of high-rise buildings. Fifth, building-specific information, such as the length, width, height, structural type, number of stories, square footage, number of occupants, and the location of buildings. The sixth data category is disaster statistics. These are mainly we are referring to natural hazard maps. 7. Disaster characteristics, such as the disaster type, track, spatial hurricane wind data, floodplain boundaries, flow data, earthquake latitude, longitude, depth, and magnitude, storm wind speed, storm category according to the Saffir-Simpson scale, volcanic eruption characteristics, inundation depth, and inundation areas. The eighth data category is the area of the impacted region. Here we are talking about the square footage of the region affected by the disaster event. Then there is the number of damaged structures, such as the number of damaged offices, schools, hotels, single-family residences, shopping malls, and hospitals. The 10th data category is the pre-disaster aerial imagery. Here we're talking about aerial photographs captured before the occurrence of the disaster. Similarly, there is the pre-disaster satellite imagery. Here we're talking about the satellite images captured before the occurrence of the disaster. The 12th and 13th data category both refer to the post-disaster, either aerial or satellite imagery, which relate to aerial or satellite images captured after the occurrence of the disaster event. The timeline associated with the data needs that belong to the amount and composition of the debris are identified to be either pre-disaster or post-disaster response phase. The second aspect is the availability of temporary debris management sites. Research related to the temporary debris management sites can be primarily categorized under two groups. Land suitability analysis studies used to identify potential temporary debris management sites locations, usually using GIS geospatial datasets, and debris supply chain optimization studies and decision support tools to determine the required number of temporary debris management sites, the locations of the sites, and the allocation of the debris. Depending on the main goal of the research, different types of data have been used, each serving a unique purpose. These data needs are grouped into 9 data categories as follows. The first data category is the hydrological data, such as the hydrography, 100-year floodplains, wetlands, coastal management zone boundaries, public wet fields, and water reservoirs. Second, geological data, such as the soil types and the seismic zones. Third, urban data, such as the land use, parcel data, protected areas, residential areas, public facilities, such as hospitals and schools, transportation networks, and utilities. Fourth, the demographics, which relate to the population count or density in the area containing temporary debris management sites. Fifth, the temporary debris management sites operational data, which cover the capacity of each reduction, separation, and recycling, or RSR technology at each temporary debris management site. The reduction proportion for each RSR technology, the proportion of the reduced debris from each RSR technology sellable as recycled material, the temporary debris management site total area, the unit processing time, and the available human resources. The sixth data category refers to the characteristics of the waste management system. Here we're talking about the numbers, locations, and capacities of available waste treatment facilities, hazardous waste disposal facilities, and landfills. The seventh data category is the feasibility constraints. Here we're talking about the minimum and the maximum number of temporary debris management sites. Then there are the debris characteristics in terms of the debris composition and debris source locations. And the final data category is the debris logistics. Here we're talking about the serviceability of the transportation network, distance between debris sources and temporary debris management sites, the number of available collection vehicles in a day, the capacity of the collection vehicles, their total working time in a day, the total removal time limit for debris from all sources, and the proportion of debris that is eligible to be treated with each RSR technology. The timeline associated with the data needs that relate to the availability of temporary debris management sites are identified to be mainly pre-disaster, with only the debris characteristics and debris logistics categories identified to belong to the response and short-term recovery phases, respectively. As for the hazards and environmental concerns aspect, their associated data from the literature either serves for detecting hazardous constituents in the debris stream, including asbestos-containing materials, chromated copper arsenate-treated wood, gypsum, sheetrock, mercury, polychlorinated biphenyls, freon, and radioactive materials, or studies that analyze the environmental impacts of the disaster debris management system, Here, environmental cost evaluation and life cycle assessment are usually conducted to calculate the environmental burden by tracking the pollutants released during the debris transportation and treatment, in addition to the greenhouse gas and energy savings achieved from recycling rather than manufacturing materials from virgin sources. The identified data needs under this aspect have been grouped under 5 data categories. The first one relates to the contaminants in the debris stream. Here we need data such as the building registers, we need field sampling, the testing of pest presence, handheld XRF units to detect CCA treated wood, the mobile radiation detectors to detect debris contamination with radioactive material, and the detection of mercury, polychlorinated biphenyls, and freon. The second data category relates to the pollutants released during the debris transportation. Here we are talking about the carbon emissions of transportation vehicles, the distance between the debris sources, temporary debris management sites, and recycling or landfill facilities. The third data category refers to the pollutants released at the temporary debris management sites. Here we are basically referring to the carbon emissions from the temporary debris management sites. The fourth data category refers to the pollutants released at the debris disposal facilities. Here we need data such as the oil usage of the heavy machinery, the consumption rates of electricity and water in recycling facilities, carbon emissions of incinerators, carbon emissions in landfills, and the decomposition of biomass in landfills. And lastly, the last data category refers to the debris recycling environmental benefits data. Here we need data such as the mass of materials recovered, the greenhouse gas savings, the energy required to manufacture recycled materials from virgin sources. The timeline associated with the presented hazards and environmental concerns data needs span across both the pre- and post-disaster phases. Moving on to the economics aspect, it has always been incorporated in the disaster debris management research, particularly in studies that evaluate the efficiency of the debris management process, optimize debris cleanup and treatment, or develop a decision support tool for post-disaster debris management operations. After a detailed analysis of the economic studies, the data needs are grouped into 4 categories. The first one, the debris transportation cost data, such as the distance between the debris source, temporary debris management site, and recycling or landfill facilities, the fuel costs, the truckload capacity, the unit hourly cost of truck operation, the hourly labor wages, the number of trips per day, and maintenance and repair costs. The second cost data category refers to the temporary debris management site cost data. Here we need data such as the fixed cost of opening each temporary debris management site, the hourly labor wages, the handling costs, cost of operating each RSR technology at each temporary debris management site, the cost of debris shipping and drying at these sites, which is usually computed as a function of the moisture content of the debris. The third data category relates to debris recycling cost data. Here we need data such as the fixed cost of installation of recycling plants, the cost of operating each technology at each recycling facility, the recycling rate, the landfilling rate, and the hourly labor wages at treatment and disposal facilities. And lastly, we need the debris recycling revenue data, such as the volume of the sellable material recovered or recycled, and the unit price of recovered or recycled materials. The timeline associated with the data needs all fall under the post-disaster period, as the costs associated with managing the debris and the potential recycling revenues are dependent on the unique characteristics of the generated debris and local conditions, such as the location of the disaster-impacted area and the market conditions. For the fifth aspect, which is the social considerations, it was found that there is a limited work on social considerations associated with disaster debris management, with mostly qualitative and few quantitative investigations. The data needs are grouped into 4 categories. The first one is the levels of social capital. Here we are talking about the structural social capital, meaning the bonding, bridging, and linking. and the cognitive social capital, meaning the trust, interaction and exchange, and social participation. The second data category relates to the public involvement in the debris operations. Here we are talking about the factors influencing the willingness of the public to support plans for their government to accommodate disaster debris, in addition to the amount of debris processed by the community members. Third, the status of the debris removal operations. Here we are mainly referring to the total debris removal time. And lastly, the recycling social benefits, usually assessed using the number of the job opportunities generated during disaster waste recycling. The timeline associated with the societal data needs all fall under the post-disaster recovery phases. Finally, the investigation of funding policies associated with disaster debris management was found to be highly limited, with the lowest number of studies identified in the literature under this aspect. The two main categories of data needs identified were the debris management planning. Here we are talking about the applicable laws and regulations governing the management of disaster debris in the area under study, and the category of monitoring requirements for reimbursement. Here we basically need the number of hours of actual emergency debris clearance work, documentation of the truckloads or the load tickets, and the actual quantities of debris removed and the total revenue earned from recycling. The timelines associated with the data needs included both pre- and post-disaster durations. How were all of these presented findings documented and expanded? So all of the findings given in this presentation have been reported in a review paper titled Systematic Approach to Identification, Characterization, and Prioritization of the Data Needs for Quantitative Sustainable Disaster Debris Management. This paper was published early in 2022 in the Journal of Resources Conservation and Recycling, and it can be accessed using the link listed in this slide. Next, expanding on the presented findings, SUMMEER held its first interdisciplinary workshop titled Understanding Data Needs for Sustainable Post-Disaster Material Management. The two-day workshop took place in Tallahassee, Florida on the 13th and 14th of January 2022, bringing together a total of 47 academic researchers and practitioners from both public and private sectors, with the main aim of validating and expanding on the data needs identified from the literature to comprehensively cover all data and analysis requirements for sustainable disaster debris management, in addition to prioritizing all such data to facilitate their collection amid limited resources, especially during the post-disaster phases. The workshop report can be found in the resources page in the SUMMEER website. And this concludes our virtual training module for today. Thank you for listening. And if you have any question, don't hesitate to contact either me or the SUMMEER organization via email or through the SUMMEER website. Thank you.